Hello and welcome everyone to this webinar session on synchronization of inverters with grid requirements and challenges. My name is Pankaj Dilip Aslerkar. Currently I am working as a PhD student under the guidance of Professor B.K. Panigrahi at IIT Delhi. So my research area is modeling stability analysis and control design for inverter based resources in AC microgrid. I did my masters in power system from IIT Bhubaneswar. We will start from very basic fundamentals about synchronization particular to the inverter based resources. We will see what are the issues in maintaining synchronization, in achieving the synchronization, in the modeling and analysis of whole synchronization process and design of it, and to mitigate some of these technical issues we will see a proposed synchronization scheme in the last. So let us consider this power electronic converter. The input to this converter can be any renewable energy source or a storage system that is typically in DC form, and inverter will convert it into AC voltage via ABC. So this power electronic converter has a lot of switching action, and because of that via ABC contains a lot of harmonics. So in order to meet power quality requirement and connect with the grid, we will use L filter, or it can be LC filter or LCL filter. The structure of this converter can be single phase, three phase, or it can be multi-level. I am not assuming any kind of structure. Okay, so the grid is represented by its Thevenin equivalent. It has resistance, inductance, and behind voltage, ideal voltage source VG ABC. So basically we are interested in this point. Let us call this point as a point of common coupling where inverter has to connect with grid. Let us say there is a breaker here. So what basically synchronization is that before connecting this breaker, before connecting inverter with grid, we need to ensure that on the both sides of breaker the voltages should resemble each other. Voltages, I mean the amplitude, the fundamental frequency, and the phase angle of the voltage produced by the inverter on the left side of the breaker should exactly resemble that the voltage, frequency, amplitude, and phase angle of the voltage which is imposed by the grid on the right side of the breaker. So that means the instantaneous voltages on both sides should be the same. So under this condition, if we close the breaker, there will be no circulating current flowing from inverter to the grid or from grid to the inverter. So once we close the breaker, we can have a controlled power flow action from the inverter if we maintain this synchronism under all operating conditions. Okay, so not only normal operating conditions, the requirement is that under disturbance conditions also, under transient event fault also, we should ensure this synchronization. So these disturbances include low voltage condition, high voltage condition, low frequency, high frequency, high rock off. So all these conditions are there. Those are there in the typical standards. So why under disturbance we would like to maintain the synchronism? Because inverter is already exchanging certain power with the grid or taking some power with the grid. So if under disturbance we will disconnect the inverter from the grid, then there is chance that because of sudden power change there can be instability in the grid. So in order to avoid that, it is an emerging requirement to get synchronized, to remain synchronized with the grid under disturbance conditions as well. So there are certain standards. So consider this IEEE standard 1547 2018 amendment. It says that before closing this breaker, we can allow certain band of certain frequency difference, voltage amplitude difference, and phase angle difference before closing this breaker on the both sides. So once the breaker is closed, the voltages will be same, and it has to be maintained same by means of the proper inverter control, so that we will maintain the voltage same on the both sides. So that is the requirement. So not only normal operating conditions, but as I said, under abnormal conditions as well. So recently government of India has introduced these regulations regarding how inverter should behave under disturbance conditions. So this is a example. This is the low voltage ride through capability of the inverter. So under low voltage conditions, because of faulty situations and all, so above this curve the inverter should remain connected with the grid, and below this curve inverter can trip. So let us say voltage has dropped down below 0.15 per unit, then it can trip. Or but suppose it has dropped down to this much level, the 0.15, then it should remain connected with the grid till 0.3 seconds. So this is a huge time. So we should have this capability that we should sense this voltage and feed back to the inverter, and inverter should produce the same voltage level at this point. So we have to design a closed loop control system. So if there was a synchronous machine at this point, we will achieve it by physical properties, means by adjusting governor settings or exciter settings of the synchronous machine. But inverter don't have such properties of its physical properties of its own. It behaves the way it is controlled. So we have to design such a closed loop control system that synchronization is maintained at the PCC. So consider a closed loop control system where we have a plant and it has a parameter x which is to be tracked to a certain reference quantity x reference. So we will take feedback, we will calculate error, give it to controller, and controller gives such a control action on plant that it will track that parameter x to reference value. Well, if we see the transfer function from error to the reference signal, then it is like given by this formula where and in its inverse Laplace will give time domain expression for error. So our objective here is that design controller C of S in such a way that error as a function of t goes to 0 as time progresses, as time t goes to infinity. So design of controller depends upon plant parameter, the feedback parameter, as well as the parameters of reference signal. So what internal model principle says is that whatever dynamics are there in the reference signal, that should be present in the loop gain C into P into H. So I will repeat, this loop gain must contain the dynamics which are present in the reference signal so as to achieve the tracking. So this is a necessary and sufficient condition for synchronization as well as or in general tracking in case of LTI systems. So we know certain things about our reference signal. Say our reference signal nature is sinusoidal. So in that case, its Laplace transform contain this dynamic Cs upon a square plus omega naught square, where omega naught is a fundamental frequency. So what is the requirement as per internal model principle is concerned is that this loop gain should contain this term S upon a square plus omega square with some gain. So under this condition only the tracking will be perfect, the error will go to 0, otherwise no. So this is the necessary and sufficient condition. So what is happening basically here is that at S equal to j omega naught at fundamental frequency, the error is becoming the gain of this term is becoming infinite. So because of this, C into P into H has value infinity, and the transfer function E of S divided by X ref of S has value 1 by infinity, which is 0. So that's how the error is going to 0. So error is becoming infinity at the frequency of reference signal. Now if the frequency is DC, then that is a regulation problem, then reference has 1 by S term in it, so CPH must have 1 by S term. Generally plant and feedback are not in our hand. We should design controllers that it should contain the desired term 1 by S or this term whatever. So we need to design such a the controller in accordance with the reference signal. Say our reference signal is a ramp, then we should design controller that contain term 1 by S square, which is the Laplace transform of the ramp. So that is the requirement. So but what if we want a certain controller dynamics and we don't want to add additional dynamics which in accordance with the reference signal? So basically we have certain reference, but we have a desired controller and we don't want to make changes to our controller for certain reasons. So what we will do here is that we will see the internal model principle in another perspective, the other way, that Instead of designing controller in accordance with reference signal, we will design the reference signal in accordance with our controller. So this is the alternate perspective on internal models principle. So we will use some kind of transformation at the reference signal. Well, so at this point here there is a comparator, and we cannot compare apple with banana, so we have to use transformation in the feedback path as well. So we are transforming we are taking controller to a different domain by using a transformation, taking to a different reference frame. So controller will produce some action, and it will we cannot feed it to plant directly because we have used transformation. We need an inverse transformation. So here what we are doing is we are taking controller to a different reference frame altogether, and we are designing this transformation or inverse transformation in such a way that internal model principle is satisfied from the point of view of controller and the transformed reference signal. Okay. So let us see some of the transformed domains in the context of our problem, which is synchronization. So this is the natural reference frame. So reference frame means the frame in which our controller is lying. So this is natural reference frame. For single phase system there is only one phase, A phase, and for three phase system we can have A, B and C, three phases. So we denote this instantaneous voltage vector, that is the representative of the grid voltage. So it has certain magnitude Vm, and it has certain angle omega t plus phi with respect to a reference axis. And in the natural reference frame, so why it is natural? Because the grid voltage is naturally occurring in this frame. So if we project this vector onto the a axis, then we will get the expression for time domain expression for this A phase signal. Similarly, in three phase case we will project it onto the B axis and C axis, and we will get their expressions. So this is without any transformation. So this is what naturally signals are. So these are, you can see, these are sinusoidal signals. This instantaneous voltage vector rotates with respect to time at a synchronous speed omega t, and these are sinusoidal signals. And for sinusoidal tracking we need a resonant controller as per the internal model principle. But what the problem is here is that we have in single phase case one axis, in three phase case three axis, and we have two kinds of power, real and reactive power. So if we see our system, we have certain voltage imposed by the grid, and we have to receive that voltage as it is. And in order to exchange power with the grid, we will have to control the current flow from the inverter. So in order to control the real power and reactive power separately in a decoupled manner, we would like to have certain decoupled components of the components for real power and reactive power in the currents, so that components are two in number, and we cannot solve expressions for those two currents separately if we have one axis or three axis. We need two axis for that. So for that we will transform that single phase or three phase signal into two axes. So one axis along the A axis, which is alpha axis, and one axis orthogonal to it, which is the beta axis. So because of orthogonality in between alpha and beta, we will obtain certain kind of decoupling in the real and the reactive power, and the decoupled control is possible. So we'll do this transformation. So how we will get this alpha and beta in single phase case? Just by transforming this internal instantaneous voltage vector onto alpha axis as well as beta axis. So we will get these expressions. Similarly, in three phase case, by projecting instantaneous voltage vector onto alpha and beta axis, we will get these expressions. Okay, so what is the transformation used for single phase case? It is the orthogonal signal generator we have to use. So A phase is same as alpha axis. So for alpha there is no need of any transformation, but for beta axis we have to need an orthogonal signal generator in single phase case. In three phase case we need the Clark transformation from going to ABC domain to alpha beta domain, and for inverse inverse transformation we will use inverse Clark transformation. Okay. So in previous case we saw that expressions for voltages are sinusoidal in nature, and in order to track those voltages we would have proportional and resonant controller as per internal model principle. But what if we want to design a PI controller? So well, why we will choose a PI controller, that we will see next. But suppose we want a PI controller. So for PI controller, as per internal model principle, we should have a reference which is constant. But our the naturally occurring signals are sinusoidal in nature. So what we will do, we will transform that reference into another domain. We will take the we will design in the controller in transform domain. So what we will do, we will choose our axis which are obviously orthogonal to each other to have decoupled control flow, but that axis are rotating along with the instantaneous voltage vector. So say instantaneous voltage vector is rotating at a speed omega t, then our axis which are d and q should also rotate with the same speed as that of instantaneous voltage vector. So if we do that, then what we will achieve is that we will in this dq frame we will see the instantaneous voltage vector as a constant, not rotating. So what we are doing basically, that from a phase, or it can be ABC phase, we are going to alpha beta domain, which is nothing but an orthogonal reference frame. So this orthogonal reference frame is stationary, so we see the instantaneous voltage vector as a sinusoidal. But again, we will rotate this alpha beta axis with the same speed as that of instantaneous voltage vector. So we will go into dq domain, and we will see the instantaneous voltage vector as a constant. So in three phase case, the same thing. By Clark's transformation, we will go to alpha beta domain, and by rotation, synchronous rotation, we will go into dq domain. Okay, and for inverse transformation, we will rotate back, and we will do inverse Clark transformation. Okay, so this is the rotating reference frame. Well, why do we choose the rotating reference frame? Why we are fascinated about the PI controller so much as compared to proportional resonant controller? So it is because of this reason. If you see the Bode plot of PI controller, so what is our requirement basically is that, so at the frequency of reference signal, we should have the controller gain as infinity, so as error will go to 0. So if you see the PI controller, if you see the 0 frequency, it has infinite magnitude, and the rate of change of magnitude as the frequency deviates from 0. So the rate of change of magnitude is very very low, I mean, as compared to proportional resonant controller. So if there is a slight variation in frequency, the gain does not change that much. But in case of proportional resonant controller, it is a kind of impulse. If frequency slightly deviates from the omega naught, the fundamental frequency, then there is sudden reduction in the gain. So that is the disadvantage. Okay, so what is the solution for that sudden reduction in gain? Then we will have to expand these boundaries of the proportional resonant controller. So for that we will use a damp resonator. But if we use damp resonator, then at fundamental frequency we will have a reduced controller gain. So that is a disadvantage. So the tracking performance will not be that much effective. So because of this reason, PI controller is mostly preferred, and accordingly the synchronously rotating reference frame, or the DQ frame, is mostly preferred. Well, as you know, unbalanced faults are most common in the system, so we can have negative sequence component as well in the signal. So in three-phase system, after Clark's transformation, if we go to alpha beta domain, in case of negative sequence component is there, the alpha beta is no longer orthogonal. So because of negative sequence, there is a mutual coupling between positive and negative sequences, and because of that we will have non-orthogonal axis. So if we just rotate the alpha beta axis by omega t and by minus omega t, we will not get the decoupled values of positive and negative sequence components. So what we have to do, we have to do some filtering and decoupling action, so that we will separate out the component of negative sequence from the positive sequence, as well as the vice versa, and we will get decoupled sequence frames, dq positive and dq negative. So if you do this decoupling, we will separate the instantaneous voltage vector into a positive sequence component and a negative sequence component. And if we project that onto d plus q plus axis, then we will get this expression. The negative sequence components also we will project onto d minus q minus axis, we will get this expression. Yeah. So next we will see the synchronization process by using this frame transformation. So for balance case I am showing. So this ABC signal after clock transformation going to alpha beta, and after rotation we will go to the rotating reference frame D and Q. So what is our objective in synchronization is that we have to synchronize the reference frame of our system, say, or controller, to this instantaneous voltage vector. So what do you mean by that? Let us take some axis like D or Q axis. It depends upon convention which axis we are taking. Say D axis we want to synchronize with instantaneous voltage vector. That means the angle between D axis and the instantaneous voltage vector, we want to make it 0. So if so happens, then magnitude of D becomes equal to Vm, and the orthogonal component Q tends to 0, Q becomes 0. So a synchronization problem is converted into a regulation problem, a tracking problem, where Q has to be tracked to 0. So this tracking we will do by a PI controller as discussed earlier. So in steady state, if Q is 0, we know that output of this PI regulator has to be some constant. So let us assume that PI controller output is the frequency of rotation of this D axis, which is the same as instantaneous voltage vector frequency, and after integrating this frequency we will get the required phase angle of the, which is same as the angle of voltage, phase angle of the voltage that we wish to synchronize. And the same angle is used for rotation, which is used in the transformation process. So this becomes a kind of closed loop control system. So in steady state, what happens is that Q tends to 0, D becomes Vm, the magnitude of voltage, this is the angular frequency of rotation of the voltage vector, and this is the phase angle of the voltage vector. So we will get all these three quantities, and we will match our reference frame with the instantaneous voltage vector, or the PCC voltage quantities are tracked. So this is how we will achieve the synchronization in steady state. So let us see some issues in synchronization. So we saw the synchronous reference frame PLL. Its input is ABC signal and or a phase signal, and we are transforming it and converting and achieving a Q component. So we can represent for a small signal perturbation, we can represent that in terms of parameters of the input signal, which is the phase angle as well as voltage amplitude. So this is equivalent representation of frame transformation, and we can have this transfer function between estimated phase by PLL and actual phase of the grid PCC voltage. So this is same as that of transfer function between estimated frequency and actual frequency. So we can see it depends upon the grid voltage amplitude Vm. So as Vm decreases, so as there is a fault or something, Vm decreases, so there is a reduction in PLL bandwidth. So what is the impact of this thing? That because of reduction in bandwidth, the response of PLL becomes sluggish. So as we can see here in terms of eigenvalues also, as the voltage level decreases, the response become oscillatory, and the damping reduces, the settling time increases. So this is one issue. So our grid is not ideal, it has certain impedance, And so this is the complete closed loop control structure. So we are sensing this V0 ABC and giving it to PLL, estimating the phase angle. So by making use of this phase angle and the reference D and Q axis references of the current, we are implementing the current controller in DQ frame, and the output is in ABC frame. So we give the reference signal VI ABC. We tell the inverter that produce this much voltage at this terminal voltage, so that the current injected by inverter IABC matches with that in the DQ reference frame IDQ reference. So it injects the current. Well, it is okay if there is no impedance in the grid, but if there is impedance in the grid, then what happens? That injected current affects the PCC voltage because of presence of this grid impedance. And as we can see, the relation is kind of positive feedback. So this whole control structure with a positive feedback, it can destabilize the whole control system. So we can see by small signal stability analysis, model analysis, that there are certain unstable modes and that participate in the PLL state. So this destabilization is mainly because of PLL parameters, or not properly tuned PLL parameters. So we have to consider the grid impedance as well while tuning the parameter. So we have to take care of this grid impedance. Well, this while designing while planning this inverter integration to the grid, we need to consider what is the short circuit ratio of the grid. So short circuit ratio is nothing but an indicator of this grid impedance. It is inversely proportional to grid impedance. So it is a relative term. So it depends as grid short circuit MVA divided by inverter rating that we want to integrate. So as the current injected increases, this impact of feedback increases. Also the impact depends on the grid strength, which is inversely proportional to grid impedance. So as per Indian grid code, we should have SCR greater than equal to 5 for integrating 10 megawatt or more inverter rating at 33 kV voltage level. Not only dynamics of the grid impedance, but also there are other dynamics that can interact with PLL. So the PLL timescale is basically a low timescale as compared to current controller and PWM switching. So in that timescale, as the grid dynamics are there, as well as there are DC side dynamics, there are some supervisory control structures. There can be another inverters in the system with, so the dynamics of them can interact with the PLL. So these various control interactions are there, and while designing this PLL structure, we can design it with respect to the known dynamics, which are the DC link dynamics are typically known, or maybe we can know supervisory control loop some parameters of it, but we don't know the grid impedance and the detailed data of other power electronic converters. So our PLL has to be robust enough to handle these interactions. So this is one of the issue in designing the synchronization scheme. So previously we saw the synchronization performance or stability of it depends upon the grid voltage level. But voltage level, when we talk about it, is the positive sequence voltage level. There is also a negative possibility of negative sequence appearing because of fault conditions. So under that case, we need to consider that also. So we need to design the PLL in a decoupled double synchronous reference frame PLL reference frame DDSRF. So in that frame, if we do the design and study the inverter control system and all, what we observe is this graph. So the dependency on grid voltage level and the unbalance factor as well. So there is certain unstable region because of presence of the grid impedance LG. The resistance can be negligible. So I have considered only impact of the grid inductance. So what happens is that generally when we are planning for some integrating the inverter with the grid, we do the planning at the rated voltage levels, so with zero unbalance factor typically, and we found out certain stability criteria that beyond this LG there can be an instability. So we design our PLL system accordingly. But what happens when there is a fault or low voltage situations? so we do not consider that when we talk about the short circuit ratio and all. So as we can see from this study is that as the voltage level falls, we can move into unstable zone when as compared to the rated voltage level. So this is one of the drawbacks. So we have to take into account the lowest possible voltage level that we are planning as from the low voltage ride through capability. So that we have to consider while designing the short circuit ratio and all. So not only voltage level of positive sequence but also the unbalance factor matters. So if we design some LG critical value after which instability occurs, and we say that okay, say 200 for this much, or say for 200 this much LG is okay. But what happens as the unbalance factor increases for the same voltage level? If you go more into unbalanced region, then we will get unstable zone, so synchronization will be lost. So we not only the positive sequence voltage level, we have to consider the negative sequence component as well, then the worst case unbalance factor scenario. So unbalance factor can be one, for example, in open circuit fault in one condition, or there can be single pole tripping. For ungrounded system, the voltage unbalance factor can be 1. So we have to consider all this situation and make the design consider the SCR for the worst case scenario of unbalance and fault. So in this study I have taken 30 kilowatt inverter interface with 400 volt grid. It has this L filter of 1 millihenry. So I am assuming that inverter is only injecting positive sequence component. It can inject negative sequence component or reactive component as well. So according to low voltage ride through capability, reactive power should be injected after a certain voltage level. So if you consider that this the lower region graph is shifted slightly upwards, so that thing is observed, that I have not shown here, but the conclusion remains same. The performance or the stability region depends on voltage level as well as unbalance factor. Yeah, so for this model I have considered 17th order state space model of the grid connected inverter, and it is verified also with the time domain simulation, this stability region. So there is requirement of analyzing and designing the control system in decoupled double synchronous reference frame in case we are considering the unbalance. So we have to do this transformation ABC to DDSRF. So it involves some this filtering and decoupling actions. Then we are designing controller plant feedback, and we have to do inverse transformation. But the key difference in between a balanced case transformation and unbalanced case transformation is that here in unbalanced case the extra thing which is there, which is this decoupling and filtering action. So this transformation and inverse transformation, the impact of them get cancelled to each other in the overall loop, but we are including more non-linearity as well as time dependence in the system. So as we linearize this system, the steady state, if you see the steady state of the system, it is no longer a constant, it is time varying in nature because of these terms. So because of time varying nature, we don't have steady state point but a steady state trajectory, and around which we have to linearize for the small signal stability analysis purpose. But obtaining the steady state trajectory itself is not possible by any means, like by analytical method or numerical method. We have to do time domain simulation in certain cases. So in particular case we can do it, but not in general. This is one issue. But well, even if we obtain steady state trajectory, there is if we get the small signal model, that small signal model is linear time variant, it is not LTI. So standard tools and techniques of LTI do not apply. There is no meaningful indices such as bandwidth or time constant or stability margin, gain margin, phase margin. So there are no such indices in case of LTV systems, and the methods of stability analysis are also, they do exist, but they are approximate. They are numerical, only numerically the solutions are possible, and they demand huge computation. So these are some of the challenges in modeling and analysis. So if we the last case slide, I have shown the system grid connected inverter with unbalanced and all. So that stability analysis is done by using these numerical tools and techniques only for the linear time varying systems. That was not an LTI system. Yeah, another problem with unbalanced grid synchronization is the voltage amplitude level issue. So in as we saw in balance case, the transfer function depends upon voltage level. But what we can do to mitigate that is we can just divide by estimated amplitude by PLL, so as to cancel this impact of this VM. So here we are basically cancelling that impact, and we are getting rid of the VM term here in the transfer function. So we are getting rid of voltage level issue, and performance is same for all the voltage levels. In balanced case, that is okay, that works perfectly fine. But in unbalanced case, what happens is that this D and Q, which are estimated by the PLL, that becomes state variable because of decoupling and filtering actions involved. So because of this, these are state variable, we are introducing some more nonlinearity into the system. And if we analyze that, the small signal stability, or if you see the eigenvalues, so in case of unbalanced case, there are no eigenvalues, but there are equivalents of eigenvalues for LTV system. So those are called as Lyapunov exponents. It is a Lyapunov based method. So those, if you see those eigenvalues, they are close to the imaginary axis, and so the performance is very sluggish if you implement amplitude normalization in that case. So yeah, so another issue is the design trade-off in PLL algorithm. So if you see in literature, there are like hundreds of PLL algorithms do exist. So but they have certain drawbacks. So consider this single phase signal. It is distorted with a lot of harmonics, noise. It has a sag and transient and all those things. So if you see different PLL algorithms for single phase case, so we have shown the response of them here. So consider second order generalized integrator PLL, which is used for single phase systems. So every kind of PLL has certain parameter to tune. So there is some parameter zeta, which is say damping ratio in case of SOGI PLL. So this component basically decides the bandwidth of the orthogonal signal generator part in the single phase system. So if we want that in steady state, there are a lot of harmonics, and we want that steady state should not be oscillatory, then what we do, we will design our bandwidth of the OSG OSG very low, so that the steady state is smooth, not affected by the harmonic distortions. But what if we want the fast performance from the PLL, like in case of faults and all, we want fast synchronization. So in that case, if we have to increase the bandwidth, but the transient performance is fast, but the steady state performance has deteriorated, as we can see here. The same thing happens for all kinds of PLL, IPT, inverse power transform based PLL, or enhanced PLL, or whatever PLL is there. So they have certain parameters, and that parameter we can choose one value for them, and whatever value we choose, depending upon that, there is a trade-off between the transient performance and steady state performance. So trade-off between speed and accuracy. So that is very common in all kinds of PLL systems. So the main problem with PLL was the transformation from natural reference frame to the DQ frame, or DQ plus minus frame. So what if we design such a transformation that it is so fast that the impact of transformation on the basis of time scale, we can neglect it for the further analysis. So so that we will not have any controller interaction problem, or we will not consider, we can neglect the dynamics of that transformation process. So can we do that? So what is our requirement here is that design a fast transient response, but simultaneously considering trade-off, we have to assure that there should not be steady state oscillations in the steady state component. So you will design the PLL in an alternate way as a parameter estimator. So consider this proposed method where a single phase single phase signal we can decompose into two parts like this. So say sine omega t component is Vd, cos omega t component is Vq, and we can have a d and q axis, so those represent the d and q components. So what the problem here is that to estimate this d component and q component, so in order to do the transformation, so here what I am doing, I am avoiding the in between Clark transformation and alpha beta domain. So this orthogonal signal generation part I am avoiding. So I am directly estimating from the given signal the d and q axis component, so that so as to hope to achieve a faster response. Well, so how to do that? So let us combine it represent it as a product of two vectors, one known and one unknown. Well, here this omega t, that is coming from PLL for the transformation process. So for transformation process, we assume that the omega t phase angle is known, and the d and q axis parameters that we have to estimate as a parameter estimation scheme. So we can use a gradient descent technique. We can define this error, the actual signal and the reconstructed signal based on estimated parameters v minus v hat. So this we can consider this kind of cost function epsilon square by 2, and this is the gradient descent principle. We can design this estimator. The if you see the time domain response of estimation error, it is given by this equation, and we have to satisfy certain condition in order to have this estimation going to 0, very similar to the internal Ward loop principle in case of LTI system. So this is no longer an LTI, this is non-linear and adaptive kind of system. So here we have to ensure another condition, which is persistence of excitation. So in this case, particular case, persistence of excitation is satisfied, so we can guarantee that estimation error goes to 0 as time progresses. So here, as we know that for large gain, if we select the large gain gamma, then we will have faster transient response, PD convergence, but poor disturbance rejection in the steady state. On the opposite, if you have small gain, we will have better disturbance immunity but slow transient response. So somehow, if we can combine these two features, that during transient we will choose large gain, and as the steady state approaches, we will choose the small gain. So we can vary this gain adaptively. So in order to do that, we can formulate the problem as a recursively square parameter estimation. So instead of just epsilon square by 2, we will define this cost function as integral of error square by 2. So well, how to solve this problem? By equating gradient of that j with respect to unknown parameters, setting that equal to 0. Well, that gives this kind of law. Well, here we have this integrator going from 0 to t. So here we will require all the data starting from 0 to up to the present time t. We will require the signal. So that is called batch least square law. And because of large data requirement here, we avoid that law for computation saving. So we make it a recursive. We represent this equation as an equivalent dynamic system given by these two equations. So this gamma of t is a time varying gain, and its dynamics is given by this formula. So this is a recursive least square law. Where we will have a recursive principle. Now if you see the conditions that are there on the optimal optimal gain, that it should have positive definite, it should be positive definite for all the time, yeah, and it is negative semi, the gamma dot is negative semi definite, that is gain starting from initial high value, it always decreases or either remains constant, but it do not increase. So these are the properties. So as we see, gamma always decreases, but what happens when there is a transient? We don't want that gamma should be small, so we want that at a transient, at the start of transient, the gamma should be increased, reset to its initial high value, and it will follow the recursive least square law after that particular time. So reset, we have to make some reset mechanism for this purpose. So and the inherently the recursive least square algorithm, when there exists a wind up phenomenon. So as the gain gamma, in absence of transient event also, as the gamma decreases continuously, and as the gamma goes very small, we will lead to divergence. So this is called wind up phenomenon. So in order to avoid that wind up, from time to time we need to reset the gain to an initial higher value. So we have to design the reset logics accordingly. So in order to detect the transient event, we can set this logic based on rate of change of RMS value with respect to time. So it will RMS will give it is a good indicator of transient events, including amplitude, phase, frequency jumps, and all kinds of transient variations. And similarly, based upon time or a certain gain of the gamma eigenvalues, we can choose the time for which we will, from time to time, we will reset this covariance gain. So this is complete closed loop PLL structure. So here this is the transformation part. We have replaced it by direct estimation part. So we have a signal, we have estimated some signal, the error that based on recursive least square principle, we are calculating the dynamics of unknown parameters. So we are by integrating it, we are getting the unknown parameters. The gain, the learning rate or the gain here, that is adaptively varied based on this recursive least square principle. And the reset, the gain reset mechanism is also proposed based on RMS value or the certain time. So so this is for recursive least square gain resetting. This is for estimation of D and Q components, and as usual there is a PI controller, and this is the PLL part. So this gives us the phase angle which can lead to the known value of Y, which is used in the estimation process. So this is the complete structure of the proposed PLL. So this is for single phase case, and this whole dynamics we can represented as a nonlinear large signal model in a recursive form as a dynamic structure. And we can this is nonlinear system, we can do a Lyapunov analysis of it, and we can ensure the for this Lyapunov function we can show that in absence of any disturbance in the input signal, by disturbance I mean any kind of harmonics or noise, so in absence of that we will have a perfect asymptotically estimating, the estimation error will asymptotically reduce to 0. But in presence of disturbance, the the error estimation error is uniformly ultimately bounded. So that is a very reasonable performance, and very good achievement for from this structure of the PLL. Well, in three-phase case, so we have seen this decoupled double synchronous reference frame, and the parameter estimator that we have designed, that gives us basically the parameters which are the coefficient of sin omega t and cos omega t in A phase for single phase case. Similarly, for B phase case, if we relate that to this d plus q plus quantities, d minus q minus quantities, we will get this relation between the A phase and B phase parameters. So we can solve these equations simultaneously, and we can rearrange those equations in this matrix form. So dq plus minus components can be related linearly to the theta parameters that we have proposed for single phase case as by this relationship. So using the same concept, we have what we are doing, we have a three-phase ABC signal. It can contain a zero sequence component. So first we are eliminating the zero sequence component from A phase, B phase. So here we are taking the A phase, B phase only. The C phase is not required because it is a because it does not contains any zero sequence component after this. So here we are, for A phase we are repeating the same recursive least square principle. We are estimating unknown parameters for A axis and same for B axis, and by using the relation that we saw by this linear gain, we are coming to the d plus q plus d minus q minus quantities. Well, and as usual, the PLL, that is positive sequence q axis, we have to track it to 0. So accordingly we have estimated the phase angle, and the y is calculated, and that y information is used in the estimation process back here. And same reset logic and gain adaptation using recursive least square principle is used here. So same harmonically distorted signal we have taken, and we, after recursive least square estimation, we have estimated this Vd and Vq components. So by means of PI controller, Vq is set to 0 and Vd gives the amplitude of the signal, as 10 and this 2. Well, so here initially we have taken, you can see the initial gain is very high value, which is 500, and as the time progresses, because of least square, recursive least square, the gain decreases continuously, it goes on decreasing. So well, here there is some transient, and because of that transient, we have again reset the gain based on the reset logic of drms by dt, and we are getting this performance. So initially, because of high gain in the transient period, we have quickly settled down to the steady state, and even if there is harmonic distortion, the steady state response is very smooth, as we can see here. So we can say we have dealt with the trade-off, and we have made the time scales of the transformation process so fast that we can neglect it for further analysis, so that there is no coupling issues in the PLL synchronization. Well, so what happens if we choose gamma different gammas? Well, if we set at constant gamma, say 500 only, we do not vary it with respect to time, then what we see is the response of traditional PLL, whereas the fast response is there initially, but we do not vary the gamma, this blue one, then we will get oscillatory response in steady state. But what if we vary the gamma? What if we vary the initial gamma? So impact of variation of initial gamma is shown here. So you can see from these graphs here, with variation of gamma, the steady state response of in all the cases is same, the steady state is smooth, but the transient response we can choose faster and faster as we choose the initial gamma higher and higher. So we have basically dealt with the trade-off of speed versus accuracy. So without losing accuracy, we are able here to achieve the required speed of estimation or required speed of synchronization, we say, by using this recursive least square principle. So this is significance of the gain variation, gamma variation. Another thing is, here we have done reset based on dVRMS by dt, but what happens if there is no transient event and steady state continues for longer time, then as I said, there is a wind up phenomena. There is a divergence of recursive least square algorithm. So this red curve indicates that divergence. But if we reset gamma from time to time without in absence of any transient also, then we will get this normal performance as it is. So this is the response for the unbalanced case. So there is a so here there is some small unbalance, and here the unbalance has increased. There is some transient event here. So you can see there are a lot of noise and harmonics present in the signal. So we are able to decompose that into d plus q plus d minus q minus axis, and the steady state is very smooth, and the transient response is also faster. So as we can see here, so this zero sequence component here, we have extracted a lot of noise in initial phase itself. So this noise is not affecting our algorithm anymore. So this is a great advantage. So not zero sequence component, not only the fundamental zero sequence, but also the triplet harmonics and lot of noise is cancelled in this zero sequence cancellation process. So here we have used this adaptive gain as seen. Yeah, so these are some real-time experimental results. So under a normal case, when there are no harmonics for sag swell also, we have compared it the performance of proposed regressive least square RLS PLL with respect to SOGI PLL. So for same achieving the same same steady state response, we can see the difference in transient response. So RLS PLL can achieve a faster response without compromising the steady state performance. So in case of harmonic distorted signal also, we can see we can tune our RLS PLLs so as to achieve faster response in transient period, and here we can see in steady state it is not affected by the harmonic distortions and all, but SOGI PLL is affected. The blue one, SOGI PLL, is affected. So in case of voltage flicker also, you can see the response of RLS PLL is better as compared to SOGI PLL. So this is the result for phase angle jump. So RLS PLL has quickly settled down to the phase angle error to 0 as compared to SOGI PLL. That responses we can see. Yeah, so finally what we can conclude is that so with increasing abnormality and grid voltage and deep sag unbalance, so we will lose the synchronism. So what we have to do, we have to design the phase loop, block loop parameters, which is the responsible for the synchronization purpose, the PLL. We have to design it as per the changing scenario. So we need some kind of adaptive, maybe nonlinear controllers. So if you design the timescales of inner dynamics of PLL faster, then we can make it immune to the other controller interactions and disturbances. That's what we have seen here. So thank you very much. So any questions?